So let me take you through how you're going to do this molecular structure lab. So you want to read the introduction about the properties of molecules and how once we build the geometry, we can understand some of the properties. So a lot of this is already discussed in that video that you watch before you start the lab. So what you want to be able to do with this lab is to determine the molecular shape and the polarity. So the whole first sheet of this lab is what I consider to be your cheat sheet. You have all of the information given to you to follow along to predict the molecular shape or molecular geometry, whatever you want to call it, molecular structure, and the bond angles. Okay. So this is what you refer back to over and over again while you're building these molecules until you can do it without the cheat sheet. So the way that it's set up, it tells you the total number of effective pairs around the central atom. So this is around that central atom. And of course, if we were in class, I would remind you, you're just counting up the total effective pairs around that central atom. And the first video you watched told you that effective pairs are bonding pairs and lone pairs and even multiple bonds. Okay, so let's just do one on our lab sheet together and we'll see how this works. So I'm going to go down to the H3O+. So you count up your electrons and you draw your Lewis dot structure. So you need to draw your Lewis dot structures in all of these boxes, and most of them you've already drawn. So you just want to make sure they're correct because you're going to use them to predict your molecular shape. So around the central atom, we want to count up all of our effective pairs of electrons. So we have 1, 2, 3, 4. A lone pair counts as 1 and bonding pairs. So we have 1, 2, 3, 4. So let's look at our cheat sheet. So we're going over to the 4s. So we have 4 effective pairs. Now notice, we have 4 pairs with none of them being lone pairs. We have 4 pairs with 3 of them being lone pairs, 3 of them being bonding and only 1 lone pair, and 2 of them being bonding and 2 of them being lone. So let's go back and look at our structure. It's got 1, 2, 3, 4 effective pairs with 3 of them being bonding pairs and 1 being lone pair. So we come over here and we go to our 4 with 3 being bonding and 1 lone, and it tells us that our geometry is called trigonal pyramidal and that it has a bond angle of about 106.5. Okay, so let's look at how we would build this. Now I'm going to build it with my molecular structure kit, but you're going to build it with your gumdrops and toothpicks, and eventually you'll build it with your virtual program online. So if I picked out 4 bonding sites and had only 3 bonds on them. So in my kit, this little nub up here represents the lone pairs, and you can see that they set up just like a little triangle, and our sheet told us it was called trigonal pyramidal. So trigonal pyramidal is what we write. Trigonal pyramidal is the molecular geometry. And then I would build it and set it off to the side. So if we were in class, you would be building these. I would be coming by and looking at them. You're going to do the same thing. You're going to build them with your little toothpicks and gumdrops, and you need to build it first, at least the first 13 that way. So we'll talk about that in a minute. And then you have to determine whether this molecule is polar or not. So you're looking for symmetry in this molecule. So if you had the final bond on here, and if you looked at your sheet, you would see 4 with all of them bonded is called a tetrahedral with no lone pairs, 4. And those bond angles are 109.5, and that's a very symmetrical structure, no lone pairs to keep the molecule from being unsymmetrical. But if we remove and have a lone pair, that is going to give us a non-symmetrical molecule. So that molecule is polar. Okay? So that's what you need to do for all of them. And then I need to see your little built molecules. And you can build yours separately and take pictures, or you can just do a few at a time and have your structures up there. So what you're looking for is a nice structure. This is not flat. Notice that it is not flat. It does have bond angles. So if you're going to build this with your toothpicks and gumdrops, it's going to be a little more challenging because they're going to sag down, but you're trying to replicate as closely as possible this trigonal pyramidal, three-sided pyramid. Three-sided pyramid. Okay? All right. So now that's what you want to put for all of these. So I want you to build, for the first 14, I think you can build the gumdrops and toothpicks pretty easily. Then they get pretty challenging here, but you can still try. So you're going to build all of these on the computer as well as the first 13 or 14 with your gumdrops. So let's do a few more together. So these are not on your sheet, but they will be similar to what you have. So I'm going to refer back to this every time I build one so that you'll understand what we're doing. So let's build SiH4. First, we have to draw the Lewis dot structure correctly. So we count up 8 electrons, first central atom, put our hydrogens around, check, 2, 4, 6, 8. So our Lewis dot is correct. Our Lewis dot is the blueprint for what we will build. We're not going to build a flat molecule, but it's going to tell us what to build. So we count up around the central atom, 1, 2, 3, 4 bonding sites. So go back and look at our 4 bonding sites. None of them were lone pairs. They were all bonded. So 4 bonding sites with all bonded is called a tetrahedral. The tetrahedral, okay, is 4 bonded with no lone pairs. So if I went to my kit, I would pick up an atom center with 4 bonding sites. You can see that in the center, and I would put 4 bonds on it. The tetrahedral, okay, so this would be tetrahedral. The sheet tells me that. And the structure, if I was building this from my kit, I would go and pick an atom center that has 4 bonding sites. You can see the little black center with 4 bonding sites, and they are coming out at 109.5 degree bond angle. So if you put your gumdrop in the center, you then need to make sure that you try to replicate this tetrahedral with your toothpicks. Don't build me something that's flat. Remember, Vesper says valence shell. So these are the valence electrons that are combining here. Electron pair repulsion. So these bonds are repelling each other to the optimal angle of that 109.5. These would be 90 degree bond angles. They would not be as far apart as your 109.5. So there's your tetrahedral. Let's move down to SeO3. Count up 24 electrons. You would see that you had to distribute these with a double bond to get the 24. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. If we'd had single bond, it would be 26, and we would have had to make that double bond. So now we've got a double bond. So how do we count up? Well, double bonds, and you're only counting around the central atom. Don't count all these electrons. Those aren't your bonding electrons. Those are your valence repelling electrons. So here you have your valence overlapping bonding, okay? So you've got 1, 2, 3 bonding sites. Double bonds count as 1 bonding site or 1 effective pair. So when you're counting up, you could call these bonding sites or effective pairs. Effective pairs can be lone pairs, single bonds, double bonds, or even triple bonds. Okay? So if I count these, I've got 1, 2, 3. And all of them are bonded. I don't have any lone pairs on this central atom. It's not these lone pairs, it's these on the central atom. So if I go to my sheet, I go over to my 3 effective pairs. Okay? All of them are bonded. None of them are lone pairs. That geometry is called trigonal planar. And planar does mean a flat molecule. There are only a couple of planar molecules, linear, trigonal planar, and square planar are flat. Okay, the others will have some geometry to them that's not flat. Okay, so if we went to build, we go to our atom kit and we get an atom center with 3 on it. So we drew it this way, and we can draw our Lewis dot structures any way that we want. But when we go to our kit, those bond angles, if you look at 3 with no lone pairs, it says the bond angles are 120. So when you build your gumdrops, you're going to have to build those 120. So a central atom will be your gumdrop, then you'll have 120, and then you can put those atoms on the end just to be pretty. Notice if I took these atoms off the end, let me take one off that's a little easier. So here's a trigonal planar. So if I took these off, they don't affect the geometry. It's still trigonal planar. Those terminal atoms, those are the atoms that we have on the end, don't affect the geometry at all. So putting them on there is just to make your molecule look cute. So if you wish, if you're limited in your gumdrops and you don't want to put them on, it's perfectly fine. So your trigonal planar will come if you go in order. You're not going to look at this and then just stick 3 bonds on it. That's not the order. And that's some of the stuff you were doing with your Lewis dot. You were skipping the order, and that just messes everything up. So first, you draw the Lewis dot. Okay, it doesn't matter how you draw. We always draw our Lewis dot right, left, up, down. We don't make them fancy. Then we count up 1, 2, 3 effective pairs. Then we go to our cheat sheet and we find 3 effective pairs with no lone pairs is trigonal planar, 120-degree bond angle, and we build it. Okay? All right, so let's move on to something that breaks the octet rule a little bit. Let's do Krypton Tetrachloride. So noble gas compounds, noble gases are usually stable, but you can force them to make compounds. So counting up our 36 electrons, putting our chlorines around, we find that that would give us 32 electrons, and we need to use 36. So this is where we are breaking the octet rule. But the central atom, being krypton, is certainly well below the 3rd energy level. So it has empty d orbitals and can hold extra electrons. So we plunk them, and we put them on opposite sides. So that's where they would repel each other. So they're not going to hang out close to each other. So they tend to repel each other. We don't care if you put them here and here, but just try not to put them really close together. Now you follow your sheet. So first let's count up. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 effective pairs. Remember, effective pairs are single bonds or lone pairs or double bonds. So we have 6 bonding sites, 1, 2, 3, 4, 5, 6. So let's go to our sheet, and 6 is down at the bottom. So we had 6, and 6 with no lone pairs would be octahedral. So I have a nice octahedral here. So an octahedral with all of them bonded is a nice molecule, very nonpolar, as you can see, very symmetrical. But that's not what we have. So let's keep looking. We have 6, but we have 2 lone pairs. So we have 4 bonding sites with 2 lone pairs, and it tells us that it's going to be a square planar molecule. So let's see how it becomes a square planar molecule with 90-degree bond angles. So here it is. Okay, and if we were going to take bonds off of this, we would take 2 of them that are as far away as possible. Okay, so we're going to take this one off one end and this one off the other. So there's our little nubs that are the lone pairs of electrons, and our geometry is named after the placement of the atoms, and it is indeed flat and it is indeed square planar, and the bond angles are 90 degrees. So there is our octahedral. So if we went back and looked at this, so I'm going to talk a little bit about polarity with this one as well. So here's our original 6, our octahedral with no lone pairs. All the bond angles are 90 degrees. And it's a very symmetrical molecule. Even though these individual bonds might have different electronegativities and be polar, overall the molecule is sharing the electrons within that entire space equally because it is symmetrical. So let's see what shape we get if we have 6 with 5 bonded and 1 lone pair. So we'll take one off of any end since they're all 90 degrees. And if we look, it says we have square pyramidal. So there's your little lone pair. And the reason that it says the bond is less than 90 degrees is this lone pair is going to repel a little more, and you can't do that. You could probably do that more with your toothpicks. These bond angles are set, but it kind of squeezes these 90-degree bond angles a little further away from it and creates slightly less than 90 degrees. So your square pyramidal will come if you had 1 lone pair. The square planar was when we had 2 lone pairs. So let's go back and look at our polarity. So here we were symmetrical, nonpolar, but our square pyramidal is a polar molecule. It is not symmetrical in nature. You have a positive end up here and this negative lone pair of electrons down here, so it is polar. Our square planar with 2 lone pairs is back to being nonpolar. Those 2 pairs of electrons are 180 degrees away from each other, so we have a very symmetrical looking molecule. If your lone pairs are opposite of each other, then they're not going to affect the polarity. Then, if we had 3 lone pairs, so we'll take another off, that gives us what is called T-shaped, and you can see it looks T-shaped, which is why it's called that. Notice, though, your 2 lone pairs of electrons are not opposite of each other. So you would not have, and actually you have 3 lone pairs of electrons, and they are actually not symmetrically arranged away from each other. You would definitely be squeezing this bond even closer here a little bit. And your T-shaped molecule is definitely polar. If you took that last bond off, now you have a linear molecule. But you have 4 pairs of electrons around the center that are all balancing each other out. So now this molecule is back to being nonpolar. The whole molecule has no positive or negative end. So 6 with 4 lone pairs would be linear. The bonds would be 180 degrees apart, and that would be a nonpolar molecule. If you had 3 lone pairs, remember that is T-shaped. T-shaped will always be polar. It's never going to be anything but polar because of the negative end of this molecule compared to the positive end. Okay. Square planar now becomes nonpolar because your electrons are 180 degrees and your bond angles are all equivalent. So that is nonpolar. Then you go back to your square pyramidal. Now that becomes polar, again, because of that lone electron pair up there. And then if you have the original octahedral, it is nonpolar. So some of you, especially when you build on the computer, are going to quickly be able to see how these work, but Polarity can be challenging for some people. It needn't be. All right, so let's do a couple more structures here, So PF5 with 40 electrons would be a central phosphorus with 5 fluorines. If you count that up, that's going to equal your 40 electrons. So you've got 1, 2, 3, 4, 5 bonding sites, and all of them are bonded. So you would come over to your 5 bonding sites with no lone pairs, and that's trigonal bipyramidal. So I really want you to see the trigonal bipyramidal yourself by trying to build it with 90 and 120. You may need, when you get to these fancy ones, to go into the virtual program and use that. Remember, the use of that is described on the first video. So if you skip that first video, you're really messing yourself up. So you want to be able to go back and make sure that you can watch that first video that describes how to make your virtual molecules. But that would be trigonal bipyramidal. Let's look at another simple one, H2S. So 8 electrons. Put your central sulfur, stick your hydrogens, and then sometimes the simpler ones, the more confused students get. You've got 1, 2, 3, 4 bonding sites. Lone pairs count. 1, 2, 3, 4 with 2 lone pairs. So go to your cheat sheet. You've got 4. Here's your 4. 4 with 2 bonding pairs and 2 lone pairs gives you a bent structure. Now, if we looked at this, it looks like those electrons are 180 degrees away from each other, and it looks like it might be nonpolar, but those are not 180 degrees. So when you build, remember you were building off of a 4. So let's take our original tetrahedral 4. Okay, so this is 4 with no lone pairs. That's called a tetrahedral. 4 with no lone pairs. 4 with 1 lone pair was called trigonal pyramidal. And now 4 with 2 lone pairs, so take another bond off, is bent. And it is bent. So if you had the kit, it's going to come out bent because you're building with 4 bonding sites and 2 of them are lone pairs, and that gives you your bent structure. Notice your bent structure is less than your 109.5, and it's also less than your trigonal pyramidal. The 2 lone pairs of electrons will squeeze these remaining bonds down. I don't want to mess with my kit, but they will be slightly less, which is not something you can do with a bonding kit. They come with the 109.5, but you would learn over time that that bond angle would be slightly less. So we know water's bent. You've seen lots of drawings, and you probably just drew it that way because you saw it that way. But this is how it becomes bent. So often you will see people bending water. Water's also got a similar structure, and they draw the Lewis dot structure bent. It isn't necessary, but it is a bent molecule. Okay? So this is what you're doing with your kit. Now, when you get to some of the molecules, as I said on the back, that are more challenging, you're free to stop building them with your gumdrops and toothpicks, but you're also free to continue doing that. So sometimes molecules will get more complicated. So here we have a structure with 2 trigonal pyramidals. How would we get a structure like that? So let's look. If we did C2H4, we would have 8, 9, 10, 11, 12 electrons to work with. We would put our 2 carbons together. So we will try to build some organic structures the week after this. So this will just sort of lead you up to that. Put our 2 carbons and put our 4 hydrogens, 1, 2, 3, 4. But we don't have, that would use 2, 4, 6, 8, 10, and we need that octet around carbon to get our 12 electrons. So organic structures are pretty simple. You have to have 8 electrons around carbon and 2 around hydrogen, and these structures just come. So if we looked, we actually have 2 central atoms, not 1. So this carbon has 1, 2, 3 bonding sites with no lone pairs, and this one has 1, 2, 3 bonding sites with no lone pairs. So if we looked at our geometry, 3 bonding sites, okay, 3 effective pairs with no lone pair is trigonal planar. So we would be attaching 2 of our trigonal planars together to get this geometry. So we want to learn how to draw out our structures and how to bond them. If we had a structure that had maybe a tetrahedral and a trigonal planar, we would end up taking this off and bonding here so that we would have a molecule with 2 different geometries. This one still has 4 bonding sites while this one has 3. Now that will come up in more advanced molecules as we move through, but we want to get these first molecules straight. So you want to build these. What you're going to want to turn into me when it's finished, okay, is this with your Lewis dot structures, your geometry, your polarity, and then your built molecules beside them. When you get to the back, you're going to need to take screenshots if possible of your geometries, but I will know by the time you get to the back, you will need to use that program to build these, and the name of your structure will be fine if that's all that you want to do. All right, good luck, and we'll see how this week goes.